Welcome to a new deep dive.
Great to be here.
Today we've got this stack of notes and excerpts you sent over, and they're taking us right inside the atom. Going way beyond that simple picture we usually start with, looking at the secret blueprint of where electrons really are.
Yeah, the details. And importantly, how that internal layout connects directly to, the periodic table, that map of the elements we all know.
Right. So for everyone listening, you've likely got the basics down: protons, neutrons, electrons, maybe even balancing equations, stoichiometry.
Exactly. So now we're asking why. Why is the table arranged like that? Why do elements in the same column act similarly? It all comes back to how those electrons are arranged, organized.
Precisely. So our mission today in this deep dive is to unpack how that electron arrangement explains the patterns, the trends we see in the periodic table, and the properties of the elements themselves.
And this is really crucial groundwork, isn't it? It sets the stage perfectly for understanding how atoms actually interact and form chemical bonds.
Couldn't agree more. Feels like the logical next step. Okay, let's jump into these sources then.
Right.
So the big question the sources tackle first is, where are the electrons really? We're moving past those, simple orbits like Bohr's model, planets around the sun sort of thing.
Right, that's a bit too neat. What these notes really stress is shifting to the idea of atomic orbitals.
Orbitals, not orbits.
Exactly, and these aren't fixed paths. They're three-dimensional regions around the nucleus. Think of them as zones where there's a really high probability of finding an electron.
Okay, so less like a train track, more like a cloud, a fuzzy zone where it probably is.
That's a good way to put it, a probability cloud. It's definitely a mental shift.
It is. And how do we describe an electron state, its likely location within that cloud? The source material brings in these 4 quantum numbers.
Ah, yes. These 4 numbers, N, L, ML, and Ms, they pop out of the math, the wave functions that describe electron behavior. They act like a unique ID set for each electron in an atom.
Like an address.
Sort of, yeah. An address that tells you its energy state and the kind of region it occupies.
An address for a cloud. Interesting. Okay, let's break them down. First one is N, the principal quantum number.
Right. N basically tells you the main energy level, or shell. It's the biggest clue about how far, on average, the electron is from the nucleus and its overall energy.
Smaller n means lower energy, closer in.
You got it. Smaller n, low energy, tighter orbit. Well, tighter cloud. The values are just positive integers, 1, 2, 3, and so on. Sometimes people use letters too, L, M.
Okay, so N is like the main floor or energy level of the building. What about L, the second one?
L is the orbital angular momentum quantum number. Bit of a mouthful.
It is.
It defines the shape of that electron cloud within that main energy level. We call these different shapes subshells.
These shapes, like spheres and...
Exactly. The possible values for L depend on N. They go from 0 up to N minus 1. But we usually use letters. L00 is an S subshell, L1 is P, L2 is D, L3 is F.
S, P, D, F. Heard those before.
Yeah, they come from old descriptions of spectral lines, actually sharp, principal, diffuse, fundamental. But the key thing is the shape. L8's orbitals are spherical, P orbitals look more like dumbbells or maybe figure eights, D and F get more complex.
Okay, so N is the floor. L tells us the shape of the rooms on that floor. Spherical rooms, dumbbell rooms. What's ML, the third number?
ML is the magnetic quantum number. This tells you the orientation of that orbital shape in 3D space.
Orientation. So which way the dumbbell is pointing?
Pretty much. For a given shape, like a P dumbbell L1, there can be different ways it can point. The values for ML go from LL through 0 up to plus L.
Okay, so for LL is just 0. One orientation. Makes sense for a sphere.
Right. For PL1, LL can be -1, 0, or +1. 3 possible orientations. Think of them along the X, Y, and Z axes.
Ah, the PX, pi, PE orbitals.
Exactly. And for DL2, LO goes from -2 to +2, giving you 5 d orbitals with different spatial orientations.
Floor N, room shape L, room orientation LL. That leaves M's, the spin quantum number. Seems simpler.
It is, yeah. M's describes an inherent property of the electron itself, its spin. It's like the electron has its own little magnetic moment. There are only 2 possibilities, which we call spin up and spin down.
Up and down arrows and diagrams.
That's right. We assign them values of plus as Pauli or half. The sources mention the Stern-Gerlach experiment as key evidence for this electron spin.
Okay, so every single electron in an atom gets its own unique combo of N, L, ML, and MS. That defines its state and its probabilistic cloud.
Wow. It's a framework, yeah. I'm not saying it's exactly here, but it occupies this kind of space with this energy and this spin.
All right, so that's the framework for where electrons are. Now, how do all the electrons in a given atom actually arrange themselves within these available orbitals? This gets us to electron configuration, right?
Exactly. Electron configuration is just the specific distribution of an atom's electrons among those possible atomic orbitals.
And the sources say there are two main ways to write this down.
Yeah, commonly you'll see SPDF notation like a shorthand listing the subshells and electron counts. Or you might see orbital diagrams, which use boxes or lines for the orbitals and arrows for the electrons.
Arrows showing the spin, up or down.
Precisely.
Okay. And are there rules for how electrons fill these orbitals, especially for the ground state, the lowest energy arrangement?
Oh yes, very important rules. The sources lay out three main principles.
Yeah, let's hear them.
First up is the Aufbau Principle. Aufbau is German for building up.
Building up.
It basically says electrons fill the available orbitals, starting with the lowest energy level and going up. You build the atom's electron structure from the bottom up, energy-wise.
Simple enough. Fill the cheap seats first. What's next?
The Pauli Exclusion Principle. This ties directly back to those 4 quantum numbers.
Ah, the unique address idea.
Exactly. Pauli says no two electrons in the same atom can have the exact same set of all 4 quantum numbers, N, L, M, M, L, and S.
Okay, what does that mean practically?
The big consequence is that any single atomic orbital defined by N, L, and ML can hold a maximum of 2 electrons.
Only 2 per box in the diagram.
Right. And if an orbital does contain 2 electrons, they must have opposite spins. One must be M's plus Hund, the other M's equals Medifar. Spin up and spin down. Paired.
Got it. Max 2 per orbital, and they have to have opposite spins if paired. That prevents them having the same 4 quantum numbers. Makes sense. What's the third rule?
That's Hund's rule. This one applies when you have multiple orbitals that have the same energy, like the 3p orbitals in a p subshell, or the 5d orbitals.
Degenerate orbitals, they call them.
That's the term, yeah. Hund's rule says that for these degenerate orbitals, electrons will fill each orbital singly before any orbital gets a second electron.
So they spread out first.
Yes, they spread out. And crucially, when they occupy these orbitals singly, their spins are all parallel, all pointing the same way, usually shown as all spin up first.
Ah, like on a bus. Everyone takes an empty double seat before someone sits next to another person.
Exactly. The sources use nitrogen as an example. It has 3 electrons in the 2p subshell. Instead of pairing 2 up in one 2p orbital, it puts 1 electron in each of the 3 2p orbitals, and they all have the same spin.
That makes sense energetically too, right?
Yeah.
Electrons repel each other, so giving them their own orbital space first seems lower energy.
It generally is, yes.
Yeah.
Minimizes repulsion.
Now, the sources mentioned these rules work well, but there are exceptions.
Yes, particularly for heavier elements, like the transition metals and beyond. Sometimes the energy levels of, say, a 4s and a 3rd orbital are so close that it's more stable to promote an electron, leading to half-filled or fully filled subshells. Things get a bit more complex down the table.
Okay, good to keep in mind.
Yeah.
What about ions? When atoms gain or lose electrons, how does that change the configuration?
Very important detail covered in the notes. Let's take cations first, positive ions, formed by losing electrons.
Okay.
The rule is, electrons are removed from the orbital with the highest principal quantum number, N, first, from the outermost shell.
Even if it wasn't the last one filled according to Aufbau?
Yes, that's the key point.
Oh, okay. Removal is always from the highest shell, highest N. What about anions, negative ions, where atoms gain electrons?
That's simpler, actually. For anions, electrons just get added to the next available orbital following the normal Aufbau order.
So just continue filling up as usual?
Pretty much. Just add to the next empty or half-filled spot according to Aufbau.
Okay, that distinction is clear. Removal from highest N, addition follows Aufbau. Now, the sources also link electron configuration to magnetism.
They do, because electrons are tiny magnets due to their spin and motion. When 2 electrons are paired in an orbital, opposite spins, their magnetic effects basically cancel out.
Okay.
But if an atom or ion has 1 or more unpaired electrons sitting alone in orbitals, their magnetic moments don't cancel. These substances are weakly attracted by an external magnetic field. That's called paramagnetism.
So unpaired electrons mean paramagnetic attraction.
Right. And if all the electrons in an atom or ion are paired up, the substance is diamagnetic. It's actually weakly repelled by a magnetic field, or sometimes just shows no interaction.
Fascinating. So you can predict magnetic behavior just by looking at the orbital diagram and seeing if they're unpaired spins.
You often can, yes. It's a direct consequence of the configuration.
So this detailed electron configuration following these rules is the key. And this leads us right to the periodic table itself. The sources touch on the history a bit.
Yeah, briefly mentioning Mendeleev and Meyer around 1869, they saw patterns when arranging by atomic mass, noticing properties repeated periodically.
But the modern table uses atomic number, not mass, as the primary ordering principle, right?
Correct. Ordering by the number of protons resolved some issues with Mendeleev's table. And here's the crucial link the sources hammer home. An element's position in the modern periodic table is fundamentally dictated by its valence shell electron configuration.
Valence shell. Those are the outermost electrons, the ones with the highest n value.
Exactly those. The electrons involved in chemical bonding.
This is where it all clicks together. The quantum numbers, the configurations, they explain the table structure. How?
Look at the table structure. The period, the row number.
Row 1, row 2, row 3.
That period number directly tells you the highest principal quantum number n that has electrons in it for an element in that row. Elements in period 3 have their outermost electrons in the n is 3 shell, period 4, n equal 4, and so on.
Okay, the row is the highest energy level occupied. Simple enough. What about the group, the column?
The group is all about the valence electrons too. Elements in the same main group, the tall columns, have the same number and the same type of valence electron configuration.
The same arrangement in their outermost shell.
Precisely. Think group 1, they all end in n-class, one valence electron in an s orbital.
And elements in the same group have similar chemical properties because their outer electron setup is the same.
That is exactly it. That similar valence configuration dictates how they'll react, what kinds of ions they'll form, and so on. The table isn't just a list, it's organized by electronic structure.
That's incredibly elegant. The table is literally a map of valence electron configurations.
It is, and as you move across a period, say from lithium across to neon to SU2Pu, are systematically filling up the orbitals in that valence shell.
Right, adding one electron and one proton each time.
And that systematic change in configuration across a period is what leads to the smooth, predictable changes in properties, the periodic trends.
Periodic trends. Yes, the forces dedicate a good chunk to this, explaining why things like size and reactivity change so predictably.
Yeah, and it boils down mostly to just two underlying factors that come from the electron structure.
Okay, what are they?
First is simply the principal quantum number, n, of the valence shell. We know that increases as you go down a group.
Electrons getting further from the nucleus.
Right. The second factor is the effective nuclear charge, Zeph.
Zeph, I remember that. It's not the full charge of the nucleus, right? It's what the outer electrons actually feel.
Exactly. The positive charge of the nucleus is partly shielded or screened by the inner shell electrons. Zeph is the net positive charge experienced by a valence electron.
And how does Zeph change?
The key thing is that Zeph generally increases as you move across a period from left to right.
Why is that?
Well, as you go across, you're adding protons to the nucleus, increasing its positive charge, but you're also adding electrons to the same valence shell. These valence electrons don't shield each other very effectively, so the pull from the increasingly positive nucleus gets stronger for those outer electrons.
Ah, okay. So down a group, higher N, electrons further out. Across a period, higher Zeph, electrons pulled in tighter.
That's the essence of it. And those two factors explain most of the trends.
Let's run through them. Atomic radius, the size of the atom.
Okay. Atomic radius increases as you go down a group. That's mainly because N is increasing, you're adding shells, the electron cloud gets bigger.
Makes sense. And across a period.
Atomic radius decreases as you go across a period left to right. Even though you're adding electrons, the increasing Zeph pulls that outermost shell in more tightly, shrinking the atom.
So biggest atoms are bottom left, smallest are top right. Got it.
What about ionization energy? Energy needed to remove an electron.
Ionization energy, i.e., is the energy you have to put in to pull off the outermost electron from a gaseous atom. Endothermic process.
Yes, i.e. decreases as you go down a group. Because that valence electron is further away, higher N, it's less tightly held, easier to remove, requires less energy.
Okay, and across a period.
i.e. increases across a period. That higher Zeph means the valence electron is held much more tightly. It takes significantly more energy to rip it off.
So easiest to ionize bottom left, like cesium, hardest top right, like helium or fluorine. Okay, next trend, electron affinity. That's about adding an electron.
Yes, electron affinity, EA, is usually the energy released when a gaseous atom gains an electron to form a negative ion. It's often exothermic, so EA values are often negative.
More negative means more energy released, stronger attraction for the electron.
Generally, yes. EA tends to become more negative, stronger attraction as you go across a period. Think about the halogens in group 17. They're just one electron short of a stable noble gas configuration, and their high F strongly attracts an incoming electron.
So they really want that electron.
They do. The trend down a group is less smooth, kind of messy, but EA generally becomes less negative, weaker attraction. The added electron is going into a shell further from the nucleus, so the attraction isn't as strong.
Okay, less clear down a group, but generally increases attraction across. What about electronegativity? That sounds related.
It is related, but it specifically refers to the tendency of an atom to attract electrons when it's part of a chemical bond.
Attracting shared electrons in a bond.
Exactly. And the trend is quite clear. Electronegativity decreases down a group. Atoms are larger, the nucleus is further from the bonding electrons,
Less pull.
and electronegativity increases across a period. Higher Zeph means a stronger pull on those shared bonding electrons. Fluorine, top right, ignoring noble gases, is the most electronegative element.
Makes sense. Strongest pull top right, weakest bottom left. Finally, metallic character.
Metallic character describes how much an element behaves like a typical metal good conductor, malleable, ductile, and chemically, the tendency to lose electrons to form positive ions.
So it should follow the ionization energy trend, but inversely.
Pretty much. Metallic character increases as you go down a group because it's easier to lose that outer electron, lower IE, and it decreases across a period because it becomes much harder to lose electrons, higher IE.
So the most metallic elements are in the bottom left corner.
Exactly. Francium and cesium are classic examples.
It's really quite amazing when you lay it out. All these different properties, size, ionization energy, electron affinity, electronegativity, metallic character, and their predictable trends across the whole table. They all trace back to just those two fundamental things, the shell number N and the effective nuclear charge, Zeph.
Which themselves are direct results of the electron configuration.
Which comes from the quantum numbers and the filling rules. It's a beautiful interconnected system.
It really is. It shows how the deep internal structure of the atom dictates its behavior and its place in the grand scheme of the elements.
So let's recap what this all means. We started with this sort of abstract idea of electrons living in probability clouds, defined by 4 quantum numbers.
Right. NL, ML, MS.
We saw how electrons fill these following specific rules. Aufbau, Pauli, Hund, leading to a unique electron configuration for each element. And then we connected that configuration, especially the outer valence electrons, directly to the element's address on the periodic table.
The period gives the highest shell. The group relates to the valence configuration.
And that position, reflecting N and Zeph, allowed us to understand and predict all those periodic trends and properties, size, energy, attraction for electrons.
It really is like the atom's internal electron arrangement is writing its personality profile right there on the periodic chart.
Yeah, personality profile that dictates how it's going to interact with other atoms.
Which is exactly what chemical bonding is all about. Understanding this is the essential foundation for figuring out why atoms stick together to form molecules and compounds.
Absolutely critical for moving forward in chemistry.
Now here's something to chew on, building on what the sources mentioned earlier about those exceptions.
The Aufbau exceptions in heavier elements.
Exactly. The sources note they often happen with transition metals, where E and NS orbital energies get very close. Why might those interactions between different subshells become so complicated or finely balanced in larger atoms? Why does the simple building up order sometimes break down, leading to these unexpected, often more stable electron configurations?
That's a great question. What happens in those bigger atoms with more electrons and protons that makes the energy levels jostle around like that? Definitely something to think about as you look deeper into the periodic table, especially those middle and lower sections.